Welcome to another lesson session on finite elements, on the application of finite element procedure for solving one-dimensional structural problem. In this lesson, I'm going to solve this one-dimensional structural problem. Is a problem that is actually different from what we have been solving up till now. In this problem, we have a gap problem between our structural body and the support. So I'm going to show you how we use finite element procedure to solve this type of problem. I plan to solve this problem in my lesson by hand calculation and also by using finite element procedure on the Matlab working environment. I will also show you how to solve this problem on the Ansys software. So let me give a brief introduction of the problem we're solving in our lesson today. In this problem, we have a structural body. The total length of the body is 300 mm. The body is between two supports. At the left-hand support, I'm coming. Not really my pen. At the left-hand support, we have a pin support. Here we don't have any structural gap problem. But at the other side, the other end, we also have a pin type of support, but we have a structural gap of 1.2 mm between the structural body and the supports. In the structural body, we have a structural load, a point load, which is placed at the center of the body. The structural load pulls the body to the right, and the value of the structural load, as given in the question, is 60 times 10 raised to power 3 Newton. That is 60 kilonewton. The Young modulus of our structural body is 20 gigapascal, or 20 times 10 raised to power 3 Newton per millimeter square. So we are to solve this problem considering the structural gap between the structural body and the support at node B. So this is our finite element model, which we're told to use to solve this problem. This problem we are told to use two finite elements. Between node 1 and node 2 is one finite element. Between node 2 and node 3 is another finite element. And we see our point load applied at node 2. The length of the finite element between node 1 and node 2 is 150 mm, as shown. And the length of our second element is also 150 mm. So we're asked to determine the displacement field. That is the deformation or the displacement at node 1, at node 2, and at node 3 when the body is applied, when a load of 60 kilonewton is applied at node 2 with a support at 1.2 mm from node 3. We are also asked to determine the stress in element 1 and element 2, and also the support reaction at node 1 and at node 3. So I'm going to explain this, or I'm going to solve this problem by hand calculation. I'll show you in my next slide. So first, I'm going to solve the problem by hand calculation. Let me zoom. So this is our structural, our one-dimensional structural body, which is placed between two supports. We have 1.2 mm gap at node 3. As you see, the body is divided into two finite elements, finite element 1 and finite element 2. So the question here is, what is the effect of 60 kilonewton load on the structural body? with let's look at it first without this support at node 3. How will the load 60 kilonewton affect the structural body if if we don't have a support at node 3? The effect of the 60 kilonewton load is to stretch the finite element between 1 and 2. That is, it will pull the finite element 1 between 1 to 2 will be in tension, and the second element will be unstressed because the effect of the 60 kilonewton load is only on the first finite element, and the 60 kilonewton load we actually stretch the body by an elongation which we can calculate using the elongation formula. Elongation equals to PL over EA, where P is the force we are referring to, and L is the finite element of is the length of the finite element, E is the Young modulus, A is the cross-sectional area. This is the formula I'm referring to. So assuming we don't have support at node 3 and we apply a 60 kilonewton load at node 2, it means that the structural body will be stretched by an amount which we can calculate using the elongation formula, using this formula. So this structural load, because it's only acting on the finite element 1, our L1 will be 150 mm. So that's why I have 150 mm here. Okay. Actually, this is what we're supposed to be looking at, this formula here. The force is 60 kilonewton. The length of the body which is affected by the load is 150 mm. The Young modulus is 20 gigapascal, this value here, and the cross-sectional area of finite element 1 is 250 mm square, as given in the question. So if we compute this, we'll get 1.8 mm. So assuming we don't have support, assuming we don't have support at node 3, it means that the structural body will be stretched by 1.8 mm, which is greater than the 1.2 gap. So it means that if we have a support here, a part of the load will stretch this body to the point where the structural body just touch the support. So that value, the force that stretches the body to the point where the structural body just touches the support, let's call it P1. So P1 stretches, in this diagram, P1 stretches this body just to touch this support. The remaining part of the force, which I define as P2, will be resisted by the two bodies, not just by body 1. Will be resisted by body 1 and body 2, and it will cause a reaction at both supports. P1 causes a reaction, but the reaction is only at node 1, but P2 will cause reaction at both node 1 and node 3. So this, on my left hand side, this structural problem can be broken down into two effects. That is force P1 that stretches the body just to this support, that stretches the body to by 1.2 mm just to touch the support at node 3, and the remaining part of the load P2, which causes reaction at node 3 and node 1. So we can add these two effects together by principle of superposition to get our response of our structural problem. To get the response of our structural problem, due to the applied load and the gap at 1.2 mm. So as we can calculate the value of P1 by determining the force. The question here, the first structural model, what value of P1 will stretch this body by 1.2 mm? That's the question. So we can use the elongation formula here to get the value of P1. So if we use this formula, 1.2 mm, that is what value of P1 will give us 1.2 mm. So 1.2 mm is equals to P1, which is what we're looking for, multiplied by 150, which is the length of finite element 1, divided by the Young modulus times the cross-sectional area. So if we compute P1, we get 40,000 Newton, which is 40,000 kilonewton. So if 40,000 kilonewton actually stretches the body by 1.2 mm, the remaining force that causes reaction at support 3 is we can calculate that simply by deducting the 40 kilonewton by the total load, 60 kilonewton. So 60 kilonewton minus 40 kilonewton gives us 20 kilonewton or 20,000 newton. So here I've determined the value of P1 and P2. So P1 is the force that stretches the body just to touch the support at node 3, while P2 is the force that causes reaction at node 3. And the reaction at node 3, I term it R2. And also a reaction is also created at node 1. I term it R3. So to get the total response of this body, at node 1, the total reaction is R1 plus R3, while at node 3, the total reaction is just R2. So what we need to do now, we need to determine our reaction value. For P1, the reaction value is simple. The reaction value, R1 is 40 kilonewton. By summation of forces in the x direction, R1 equals to P1. But for the second case, we cannot determine R3 and R2 easily. We need to use some compatibility formula. Like for this question, if P2 is to act on this structural body, when the structural body just touches the support, P2 will stretch finite element 1 in tension, while finite element 2 will be in compression. So the extension in finite element 1 is equivalent to the compression or the reduction in length in finite element 2. Also, we can to denote how do we get the direction of this reaction? That's another question you would like to ask me. If P1 stretches the body, if P1 stretches finite element 1 in tension, that means the reaction of R1 will point to the left. For the reaction of node 1 will point to the left. That is R3. You can see it pointing to the left. And if finite element 2 is in compression, it means R2 will point also to the left. So we can write another equilibrium equation formula. Summation of forces in the x direction, R3 plus R2 is equals to P2. That's another formula. So we have two formulas, R3 plus R2 equals to P2, and also the deformation, which the extension of finite element 1 is equals to the deformation in finite element 2. So moving to my next slide, you'll see all what I just explained. So I told you the deformation in finite element 1, which is noted by DL1, is equals to deformation in the second element. So if we equate this, we get R3 equals to R2. And you might want to ask me another question. Why are we not considering 1.2 mm in our length formula? We're not considering 1.2 mm because 1.2 mm is a very small value, so we can just neglect it and it will not affect the accuracy of our results. So you don't actually need to consider 1.2 mm. You can still take your L1 to be 150 mm, L2 to be also 150 mm. So using this equilibrium compatibility equation, we get R3 equals to R2. And also using the equilibrium of force equation, R3 plus R2 equals to P1 equals to P2, and P2 equals to 20 kilonewton, which we have determined in my previous slide. So if we substitute this equation in this equation, we get R3 equals to 10 kilonewton, and we also get R2 equals to 10 kilonewton. So the total reaction at node 1, R3 is 10 kilonewton, this R3 here is 10 kilonewton, R2 here is 10 kilonewton. So if I should go back to my previous slide, the total reaction at node 1 is equivalent to R1 plus R3. And we know that R1 is our P1. R1 is equals to our P1. R1 is equals to 40 kilonewton. So 40 kilonewton plus 10 kilonewton, which is 50 kilonewton. So the reaction at node 1, the total reaction is 50 kilonewton, while the reaction at node 3 is just R2, and we calculated R2 as 10 kilonewton. So if the reaction at node 1 is 50 kilonewton, that means 50 kilonewton is the force that acts on finite element 1. So finite element 1 is stretched by the R3 reaction. No, it's not actually. Finite element 1 is stretched by R1 plus R3. This is what I mean. Finite element 1 is stretched by R1 plus R3, which is 50 kilonewton. So to determine the stress of so here is supposed to be R3 plus, let me write it. Here is supposed to be R3 plus R1. The same thing here, R3 plus R1. So finite element 1 is under 50 kilonewton load in tension. So to get the stress, just divide the force by the cross-sectional area, and the cross-sectional area is 250 mm square. So we get the stress to be 200 MPa. For element 2, the reaction force acting on finite element 2 is just R2, and R2 is 10 kilonewton. So we divide the force by the area, we get 40 MPa. And the deformation at node 2 is equals to the deformation is equals to, let me go back to my first slide, second slide. So the deformation at node 2 is equals to the deformation due to P1 load and the deformation due to P2 load. And the deformation due to P1 load is equivalent to 1.2 mm. We know that. But the deformation due to P2 load, we don't know that, but we can calculate it since we know the value of P2, which is what I did here. So the deformation at node 2, I say is equals to 1.2 mm, which this is the effect of the P1 load, and the second part is the effect of the P2 load, which is given by this formula. P equals to R3. Why is P equals to R3? P equals to R3, P1 load, okay. The Here I'm supposed to actually, sorry, here is supposed to be P1. Let me correct this quickly. Here is supposed to be P1. This is a mistake. P1. So P1 times L1, and P1 is 10 kilonewton. So the 10 kilonewton force times the length of the first finite element, 150 mm, divided by the Young modulus multiplied by the cross-sectional area. So this will give us 0.3. So 0.3 plus 1.2 is 1.5 mm. So the deformation at node 2 is 1.5 mm. So we are going to validate our finite element solution with the result we got from this AND calculation. So now I will move to the finite element calculation procedure. For the finite element procedure for this problem, I don't think the elimination method can be applied to this problem because of the gap variable. But if it can be applied, maybe someone can get through to me and teach me how an elimination method can be applied to this problem. I'm going to explain how we use the penalty method to solve this problem. Since we have three nodes for our finite element model, that means our stiffness matrix will be a 3 by 3 matrix. So that's why we have a 3 by 3 matrix here. And since we have support at node 1 and node 3, we add the last stiffness at 1, of the stiffness matrix and at 3, of the stiffness matrix. Also, because we have gap problem at node 3, we need to add C times the length of the gap. A is the length of the gap. At node 1, actually, this will not be there because we don't have gap problem at that point. So this is the matrix equation which we can use to determine our displacement vector Q1, Q2, Q3. So once this stiffness matrix is assembled and modified, and also the force vector is modified, we can determine our displacement vector from this matrix equation. Also, we can calculate our reaction at both support 1 and node 3 using this equation. I'm going to show you how you do this on the Matlab working environment. Let us move to the Matlab working environment now, where we'll see the solution to this problem using the finite element procedure. So as usual, I've already created a live script which I use to solve this problem. So this is the question. So the first thing we need to do, as I always tell you in my previous video, we need to define the finite element model. So we are breaking the structural body down into two linear finite element 1 and finite element 2. And the finite element model has three nodes, node 1, node 2, node 3, and it has 3 degrees of freedom. So, and once you have broken down your body into finite elements, you need to define both the geometric and the material property of each finite element. So that's what I did using this Matlab code. E1 is equivalent to the Young modulus of finite element 1. L1 is the length of finite element 1. A1 is the cross-sectional area of finite element 1. So I enter the values for these three parameters, and the value is stored in the Matlab working environment. I do the same thing for the second element, E2, L2, A2. So after I've defined this this property, the next thing is to define our local stiffness matrix for each element. So we use this formula to determine the local stiffness matrix, and we can use the material and geometry property which we've already stored in the Matlab memory. We can use it to calculate our local stiffness matrix. So K1 here is denoting my local stiffness matrix for element 1, and is equals to E1 multiplied by A1 divided by L1 multiplied by this matrix. E1 is the Young modulus of element 1. A1 is the cross-sectional area of element 1. L1 is the length of finite element 1. So this is computed, and this is evaluated to be it gives us this matrix 3.33 times 10 raised power 4 Newton per millimeter. I always work in Newton for force and in millimeter for length. That is the SI unit I work in. The same thing you do for the second element. You determine the local stiffness matrix for the second element. This Matlab could calculate the local stiffness matrix. So it gives us the same matrix as K1. So K2 is my local stiffness matrix for element 2. So now we have calculated our local stiffness matrix for both element 1 and element 2. What we need to do, we need to assemble this local stiffness matrix. And as I usually do in all my lessons, we start by generating our zero matrix, because this problem has 3 nodes or 3 degrees of freedom. It's not actually 3 nodes, because this problem has 3 degrees of freedom. That is why our local stiffness matrix is defined as a 3 by 3 matrix. So the first thing we need to do, we need to create a 0 3 by 3 matrix. So this Matlab code does that. I'm defining our global stiffness matrix to be equals to a variable called K. So I'm assigning a 0 matrix to our global stiffness matrix K. So now what we need to do, we need to add the local stiffness matrix to our 0 global stiffness matrix. K1, that is the local stiffness matrix of element 1. Element 1 is located between node 1 and node 2. So we need to add this local stiffness matrix at this position in the global stiffness, in the 0 global stiffness matrix. And this line of code, this Matlab line of code does that. So I type this code and I click on run. This gets evaluated. So you see the K1 matrix has been added to this position. We do the same thing for the K2 matrix. The K2 matrix is the local stiffness matrix of the second element, and the second element is located between node 2 and node 3. So we need to add K2 at this position. So this code does that. So when I run this code, this matrix is formed, adding K2 to this position. So this is our global stiffness matrix for this structural problem. So because we are using the penalty approach, we need to determine the value of our last stiffness, which we'll add at node 1 and at node 3. Why are we adding a last stiffness at node 1 and at node 3? We want to add a last stiffness there because we have support degree of freedom at that node. At node 2, we don't have any support degree of freedom. So we add a last stiffness to 1, 1 and 3, 3 of the global stiffness matrix. So how do we define this last stiffness? As I've said in my previous video, the last stiffness is the largest value in this global stiffness matrix multiplied by 10,000, and the largest value is 6.6667 times 10 raised power 4. So this Matlab code actually does the computation for us. The Matlab code, you see a max function. The max function actually is an inbuilt function in Matlab that 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 helps us to extract the maximum value in a set of numbers, in a matrix, in a vector. So what you just need to do is to input the matrix you want in the max function, and the max function will return the largest value in that matrix for us. So C equals to max open bracket K open bracket column multiplied by 10,000. So the C gets evaluated as 6.6667 times 10 raised power 8. So this C, as I said, we have to add it at this two position, at 1,1 and at 3,3. This Matlab code adds the last stiffness at this position here, at this position. So when I run this code, C is added to this position. Also at 3,3, this Matlab code adds C at 3,3. So C is added to the global stiffness matrix at this position. So here I redefine this is actually my modified matrix. So I say let mod K equals to K. Here mod K is my modified matrix. So I just want to give it a significant name. So I say mod K equals to K. So now I'll be dealing with mod K. Mod K is my modified global stiffness matrix, which is given by this, multiplied by 10 raised power 8. Now, after we have defined our modified global stiffness matrix, we need to define our global force vector. And our global force vector is an array of the forces acting on the structural body. At node 1, we don't have any force on that node. At node 2, we have a 60 kilonewton load pointing to the right. Let me go back to the top. You see at node 2, we have load P pointing to the right, and load P is 60 kilonewton, or 60 times 10 raised power 3 newton. So at node 2, I specify the load to be 60,000 newton. At node 3, we don't have any load, so we have 0. So I wrote this code and I click on run. F is evaluated and stored in the Matlab memory. We need to modify this matrix. That is, we need to add a value to the third position of the matrix. Why? Because we have a gap problem there. So we need to add C multiplied by the gap. C is our last stiffness. C multiplied by A. So, and here I define my A to be 1.2, as stated in the question, 1.2 mm. So if to add C times A to this position, this Matlab line of code does that. So F open bracket 3,1 equals to F open bracket 3,1 plus C multiplied by 1.2, or I can say A. That's actually why I define A as a variable. Let me put A there. A is 1.2. So you run this. So this is our modified force vector here. C multiplied by A is evaluated to be 8 times 10 to the power 8 Newton. So I renamed the force to with this line of code. Let mod F be equals to my modified force vector. So mod F equals to F. So I've stored so mod F equals to this force vector here. So now that we have defined both the modified global stiffness matrix and force vector, we can calculate our global displacement vector, and we do this by inverting the modified global stiffness matrix and multiplying that by the modified force vector. So if we run this line of code, we will get Q to be equals to 0.0001 at node 1. We're actually supposed to get 0 at node 1, but we got a very small value, 0.00001 mm. It shows you that finite element method is not a precise solution, it's an approximate solution, but the approximation is quite good. At node 2, our displacement is 1.5 mm, which we got in our hand calculation. If you remember, let me show you. And our displacement at node 3 is 1.2 mm, which is the gap at node 3. But this 1.5 mm, we calculated it in our hand calculation. I'll show you now. Let's go back to PowerPoint. So here you see DL, that is the extension. Actually, the deformation at node 2 is equals to 1.5 mm, which is what we got in our finite element solution. So let's go back to the Matlab working environment to determine our stresses in the finite element 1 and finite element 2. We should note that what we got in our manual calculation for the normal stress in the finite element 1 is 200 MPa, while for element 2 is 40 MPa. So let's see if we get the same stress value in our finite element solution. We're moving to the normal stress in both finite element now. We use this formula to compute the normal stress. So using this formula, we can calculate the normal stress with this Matlab line of code. E1 multiplied by this vector or matrix divided by L1, see the L here, L1 multiplied by the displacement vector. Because element 1 is located between 1 and 2, so this is the quantity we use for to compute our stress in finite element 1. 0.001 is our Q1 and 1.5 mm is our Q2. So I will extract these two values using this Matlab code here. So once I run this code, I get 199.9960 MPa. The exact solution is 200 MPa, but finite element solution is giving us 199.996 MPa. You can see how close the solution is. For the normal stress in the second element, we use the same formula, but the displacement quantity will be different. It will be the displacement quantity between node 2 and node 3. And between node 2 and node 3 is these two values, 1.5 and 1.2. So I use this code to extract the two values. L2 is 150 mm. E2 is the Young modulus of finite element 2. So I run this code, I get minus 40.004 MPa, but the actual value is 40 MPa. So you can see how close this finite element solution is to the hand calculation. The reaction formula using penalty method. Come here. The reaction formula is not here. Sorry. I'm trying to look for the reaction formula in this live script. I don't also have it here. Okay, this is the formula. Let me copy it and place it here. So this is reaction formula which we will use to compute the reaction at node 1 and at node 3. At node 1, we don't have gap problem, so our A is 0. So it is minus C multiplied by Q1. So that's what this Matlab line of code calculates R1 for us, and R1 is calculated as 6.4001 times 10 raised to power 4. This is like 64 kilonewton. Yeah, this is 64. This is like 64.001 kilonewton, which is close to our hand calculation. But this R3, sorry, there's a small problem here. I forgot to apply this gap. The reaction value here is not correct. It is minus C multiplied by the reaction by the displacement quantity at node 3 minus A. A is the gap and A is at 1.2. You see it, A equals to 1.2. So let me run the code to get the actual answer. So we see A we see R3 to be equals to 3.33 times 10 raised to power 9. What is going on? I'm very sorry, but I think there must be a mistake somewhere in my Matlab code, because R3 is supposed to give us 10,000 Newton, 10,000 Newton or 10 kilonewton. So let me inspect the code. Yes, our Q. This is supposed to be mod Q, and this F, I'm sure this F was not modified. That's the problem. So this F is supposed to be mod F, which I modified here. Was this? Okay, this is not the code I was using. I was using the wrong code. I was using another. Oh, I'm so sorry. This is the code I was supposed to use to explain. So let me explain the reaction again. I was supposed to use this live script. I was using another live script. So R1, as I said, is minus C multiplied by the displacement at node 1. We have our A for node 1 is 0. So that's why we're using this Matlab line of code in this manner. So once I run this, we get minus 4.9999 times 10 raised to power 5, which is very close to 50,000 Newton, which is what we have in our manual calculation. For R3, there's a mistake here. I did not consider the gap at node 3. We need to deduct A from Q3. So that's what I'll do now. I've adjusted the Matlab line of code. So let me run the code. R3 should give us something close to 10,000 Newton minus 1.001 times 10 raised to power 4 minus 10,000 Newton or minus 10,000 kilonewton. So this is how we use Matlab. This is how we use finite element procedure to solve problem with gap in one-dimensional structural problem. In my next lesson, I'm going to explain how we model and solve this problem on the Ansys working environment. Thank you so much for taking the time to watch my video. Have a nice day.